we'll be talking about the real-time data challenges, the newer data sets like the fiber optic data. I'll be explaining a few concepts about distributed computing and the cloud technology of subsurface data. Also, we'll be talking about edge computing and how we bring it all together with data pipelines and how we build contextual analysis dashboards. And then I'll be presenting a quick demo. So as we all know, the subsurface is a very complex topic where all the oil companies are always trying to understand. So you have different geological basins. There is continuously growing data. You have data users in different locations, especially in this current environment. And then you have the sequential interpretation of data sets from geophysics to drilling, and then other production workflows. But all of these are discontinuous, and over a period of time, they've improved quite a bit. But still, the problem exists. And then you have structured data and unstructured data. For example, for the unstructured data, you have text and embedded text. And for the structured data, you have SegWy, LIS, all these formats. And then you have the proprietary data formats where companies, based on the business needs, they have built their own formats because there is no existing standard or the standards are evolving. So they have in-house formats as well. So you have all these different challenges. So these are the different data types you would look at. At the field level, you have the seismic, geology, well logs, and the GIS data. And then you have the geobodies information. At the well level, you're looking at wells and multi-wells, the completions and the core samples. And on the sensor data, you're looking at fiber optic and like the distributed temperature sensing and acoustic sensing data. So you have different variety of data. And if you want to categorize, you have seismic and DAS as the high volume data. And depending on where you are looking at, whether you are getting real-time data, you need to have a data organization strategy and how you are going to bring all these pieces together. You have the newer data sets like the fiber optic data, where different data sets like the DTS and DAS, they are pretty huge. Like the DAS, for example, it generates like 5 to 6 gigabytes a second. And if you look at a typical hydraulic fracturing job, you have pretty much 1 to 2 terabytes a day. So with this, you need the power to do the computation analysis. And if you look at the real-time data, the data is continuously growing and you have remote connectivity problems. You have time constraints because you have to analyze the data quickly, and then you have limited staff. So it all boils down to how you manage this data and infrastructure and how you can do it at a very reduced cost. So over the last decade, Energistics has taken the lead in developing standards like the BitsML for data exchange for ProdML, and they have now extended for the fiber optic data. And they've also built standards like the ETP, the Energistic Transmission Protocol, where there is efficient data exchange between applications. It promotes streaming. And there is also a discovery mechanism. For example, you don't have to really have a loop that is continuously looking for new data. Rather than when the data is available, you can now pull that information. So you have different standards that are evolving, both the standards and the transmission. So this is an example of a BitsML architecture where you have a client and a server, and you're exchanging information through a standardized XML or a JSON format. So the idea is you would exactly represent the data it should be, and you also are maintaining the relationship between data. For example, you have a basin, you have a well, you have multiple well bores, and all of this belong to a particular field. You have formation tops. So all of these, the relationship of how you represent the subsurface is maintained by these standards. Then comes the real-time data transmission techniques, where you are now looking at OpenVDS, and companies like Blueware are leading the innovation in this space, where they have done a lot of compression of information, and they're able to stream data sets like Seismic, just like how you see a Netflix video. So there is a lot of innovation in the data transmission techniques, but still you still have problems with respect to how do you bring it all together, and with different data sets, how do you correlate them to have a meaningful subsurface interpretation. And in all of these, if you are constantly moving data, then you have a problem of data duplication as well. So how do we use the cloud and edge computing for the subsurface? We see there's a pattern evolving in the last 20 years of technology where we could utilize the data pipelines, the Spark cluster, the distributed computing, and also the data that is continuously changing. You can now use a DevOps approach because the data changes, the interpretation changes as the subsurface is exploited, as it's produced, the whole configuration is changing. So you need a constant dynamic update of all the workflows. So then comes the data factory microservice. So the purpose of a data factory is to move data from point A to point B, like a source and a sink, through a data pipeline. And it also assists the transformation of data. Let us say you are computing lots of data, you want to cleanse the data, all of that. So you can use microservices to do that. And then you can also automate the entire pipeline. So at the end of the day, this is providing a mechanism for all the oil companies to manage the overall data lifecycle. So for example, Amazon has Amazon Glue that provides this kind of a ETL process, the extraction, transformation, and loading. Same thing with Microsoft, we have Azure Data Factory. So let's look at the distributed computing. So if you have Spark, so the idea of Spark is when you have lots of data, you will be able to compute, you will be able to distribute the workloads across different nodes. So you have a concept of worker node and the master node. So the master node is more like a brain of how it controls the information. And the worker nodes are doing a processing, the individual processing. Let us say, for example, you have a seismic data set, which is like, say, 300,000 traces. You would be able to now chunk it in pieces, like 100K each, and then you can have 3 worker nodes that can be processed. Now, depending on how much you want to process, you can have different cluster options, like the memory optimized. If it's more of a storage problem, you can have a storage optimized cluster. You can have a compute optimized. If you're doing lots of seismic transformations and all of that, you can do that. And then ultimately, you can go into the GPU based. And then you have the RDD, which is the distributed data sets that are resilient and fault tolerant. So the purpose of this is when you don't have the exact need to do any kind of operations, you can still do all the computations. Only when you're trying to display or do all of that, that's when it does a lazy invocation of the execution in this case. So Spark has a rich support for all the different programming languages, like you have Java, you have Python, you have R, and also they support all the machine learning tools like the TensorFlow, all of these, and it's heavily SQL based, so you can have like the data transformations, data fetching, and all of that. So it has a good support for both traditional programming as well as the ML, the machine learning approach. So if you see in the last 20 years of technology evolution, after the Y2K, Yahoo started the whole distributed computing concept with Hadoop. So the applications evolved from client server to microservices. Meanwhile, the on-prem compute, like the Hadoop clusters, now have moved into the cloud-based clusters. So essentially what has happened is all the cloud providers have converted this into a managed service. So AWS has led the pack. Same thing with the Microsoft, with the advent of the new CEO, they had a cloud-first, mobile-first approach. So they have caught up with all of these. And Google is leading the way in terms of ML with respect to the tensor processing units. So at the end of the day, all of these are now provided as a managed service. So how does it translate to business? So it reduces the pain of maintaining the on-prem clusters. And the cluster setup is really fast. So you can simply subscribe, you can configure and turn on the microservices. You have high availability, and you can have streamlined I/O. You can schedule the jobs. You can build and deploy machine learning models, because typically what you have is somebody like a specialist is building a machine learning model, but they're unable to deploy at scale into the business unit. So these provide a very good pipeline for all of that. And the good part is it's pay per use and pay per compute use. And you can scale the cluster depending on the job, whether it's a store, compute, or memory optimized. So you have all this technology. So now how does it translate to actual subsurface implementation? So here is an example where you have lots of on-prem data. You have well logs, the metadata, the well information, you have core data, you have formation tops, you have subsurface data like horizons, faults, and DFNs. You have seismic, and you have the fiber optic data. So in all of these, you are now providing a bunch of data pipelines where you can move from point A to point B through the data factory or Glue, and then it's moving into a staging area here. And you apply some business tools. Here it could be like, I have duplicate formation tops. I need to cleanse some of these null values. So things like any business tools you can apply, and you can process all this information on a Spark cluster and then store it in your cloud storage, whether it's a blob or an S3 bucket. So now with the advent of all these standards, you now have an option for using APIs. So OSDU has taken the lead in terms of providing a data standard format where you can exchange information between applications. So the main goal is you have the operator data, and if they provide that into the cloud, you can now have the cloud storage. So the cloud providers now provide not only storage, but also the mechanism to exchange data between the operator and the vendors. So there has been a lot of talk about OSDU yesterday. Joe from AWS presented an excellent talk on how it works. But from the vendor point of view, at the end of the day, this becomes they're looking at how you standardize data exchange between applications, whether it's an operator, whether it's a software vendor, whether it's any consumer. And also, let us say you have a MATLAB program and you have a Java program, you have a C# program. They all exchange data with a standardized way of exchanging information through the API call. So this gives a level playing ground, and it promotes more innovation for different kinds of vendors, and also minimizes any kind of data duplication and lack of data standards. So you don't end up with custom standards. Let's look at edge computing. Like with all the data that is growing, it's probably not a good strategy to move everything into the cloud. So why do you need large-scale edge computing? For example, for the DAS and the Seismic, if you have lots of data, you need to process at the edge. And the edge should also have access to the subsurface model so that you can now have a machine learning adaptive model. So let us say you have new features that are detected, the edge should be able to get those new parameters or the new thresholds to do a new set of cleansing or new set of computations. So the workflows have to update, and you should have the ability to do a lot of what-if scenarios at the edge. And also, there should be an edge to cloud sync mechanism as well, depending on the network connectivity. And then you should also have access to many specialists across the different locations. Then all of this, you need like a unified portal where everybody can exchange information. So here is an example of why you would need an edge computing device. So you have DAS data, which is about 5 to 6 gigabytes a second. So what you see here is the blue color, which we assume that it's not required. The more interesting data is this yellow and the red colors. So you see, and this is 1 second of spectral energy that is generated from the DAS box. So as you are playing through, let me go through because I think the video is not playing. Yeah, we'll get back to the video. So the idea is the purpose of edge is to remove the noise or do any kind of edge computing that will require the cleansing of data or applying machine learning at the well location. So these are the different cloud providers that are providing these edge devices. You have Amazon Snowball, which provides this ruggedized storage. And it's basically a flexible pricing, and also it has both storage and compute. Same with Microsoft, which is providing flexible computing options. And then you have the low-end IoT devices, which are not meant for large-scale computing, but something like a well data can be gathered. So you have a typical application would be seismic and acoustic sensing. So let's look at, once you have all this data, what are the different techniques you could use? So the idea is you would go through a data cleansing mechanism. For example, you go through different steps of data processing, like cleansing, like outlier detection and things like that. So you would cleanse all of this, you could do on a cluster. So you could cleanse the data, you can apply the business rules, just like removing duplicate formations and things like that. And while the data is being processed, you can now have the metadata extracted. So for example, if you're looking at a seismic cube, you can take all the attributes, which is the header information, and they can be stored in the database. or in a relational database. So the idea is when you query, you don't have to actually pull the data, you know where the well locations are. So you can look at the metadata stored separately. And then all of this can be governed through the Subsurface portal through an integration service. And then as it is converted to the data model, all of this is managed through a managed service. In this case, it could be like a data management service that is helping the data governance. This is an example of how you would automate the process. So you can schedule a job which is taking data from on-prem to the cloud through a data pipeline. So I'll go through a demo later on. So with this option, you are now able to move the data from point A to point B. You can schedule it through a secure connection, all of this information. So essentially, the cloud microservices are helping in automating the data migration and also the data transformations. So once you have all of this, this will now enable different workflows to be able to seamlessly exchange information. So for example, you have seismic information that can go through all of this different analysis, and that same analysis can be available for a production engineer or a completion engineer, or even a geomechanics specialist that is looking at what is the overburden and so on. So you have that seamless data exchange once you have all of these aggregated in the cloud pipeline. So then you can do contextual data analysis. Like for example, here is a bunch of wells. You're looking at the subsurface information. You have the reservoir grade, you have faults, you have the production here, and this is a geomechanical model. And so essentially you're looking at what is the stress state as you're producing over time. So things like that, you can build the contextual data analysis. So now I'll go through a quick demo of all the different pieces that we have talked about. So first I'll go through the subsurface data pipeline. So we'll look at how we manage the information here. Okay. So this is the Azure portal where you're looking at the Azure Data Factory. On the left side, what you see is a bunch of data pipelines here. So you have the well log data pipelines here, the LAs. So for all the different data types, you can define a pipeline. In this case, a pipeline will have a source and a sink. So you're connecting from an on-prem, let us say it is like a NAS drive, you have SS connection. You can move from there to the Azure blob. So here is an example where I'm doing a copy of the information of LAS files to the blob storage. And before I'm doing that, I'm going through an LAS parsing mechanism, which is like a Jupyter notebook that is being processed on a Databricks cluster. And all of this is now migrated into the cloud. Same thing, you can define the source and sink. So for example, here you have the schema and all of that. So let me run a pipeline. So here is an example where I can run through a pipeline here. So I'm running through a pipeline. So the idea is once it runs through the pipeline, you are now providing a mechanism to move the data from on-prem to the cloud. So here, what is happening is I'm moving the data from our FTP site, which is an SSH connection, and I'm moving the data into the cloud. And while I'm moving it, I'm also parsing through an LAS parser. So here you're seeing the progress. And this has a lot of features. So for example, if you want any kind of transformation, you can use an Azure function or a Lambda function. You can, and these are the different transformation techniques that you can use. You can have notebooks, you have jar, all of these, and you have Python code. So essentially what is happening is here, as I'm processing through this information, you can now keep track of all the different data logs and things like that. Okay, so it gives you the goal here is to trigger or schedule a job while it is going through the process. Okay. Now this is behind the scenes when you use either a data factory or a cloud or a glue interface. So when it comes to the application itself, so you can schedule the job here itself. So for example, you can go through a secure connection, whether it's like a source or a destination, and you can have the different SFTP, all the different connections here, different databases. And then you can look at the schedules, just like what I've shown you. The same thing can be in a portal, because all of these are managed services. So you have access to these information through any kind of vendor application. So this is an example vendor application where I'm pulling that same information into our portal, and then I can help the IT to manage this moment of data. And then you can also look at the status. You can manage this information here. So that's how you can schedule a data pipeline. So as the data is moving, it is storing into a blob storage. So here is a blob storage in Azure. So what I've done is I have the seismic files here in the blob. We moved the wall data set. And then you can have the LIS files here, all the different data, different LIS files. So essentially, you're moving the data from on-prem to the cloud for further processing. So that's on the data pipelines. So now let us look at, once you move all of the data, how do you look at all these different well information? So let me go back to the portal. So I will now look at all the different kinds of wells. So here is an example where I'm looking at the well information. This is a public database from the US. So for example, we have pulled all the different wells from the USGS and also the public data sources. So what I'm seeing, what I'm querying is I'm querying all the wells from this database. It has about 1.3 million wells. So that is your data set. Same thing, you can populate this information here. You can look at this information here. You can slice and dice. So now as you are moving through, I can look at these data types. And now I can see the well information here. So what you see here is the trajectory of the well, and these disks are the changes in the formation tops. So like that, you can now look at all this information. Then you can look at the different geobodies. So for example, so you can look at the DFNs, the discrete fracture networks, the faults, and the horizons and the surfaces if you have, and any kind of other kinds of GIS information like the shale plays, and also if you have any public data, you can add it over there. So as you are moving through this information, you can now look at different data sets here. So for example, I can go here and look at all the subsurface information here. Like you can now look at, so once you have looked at the field data, you can now go inside and look at this information, like the individual basin information here. Here is a basin that I'm selecting. I'm selecting the well bore, the well, and the well bore. So again, you have the survey information here, you have the well schematic. So like that, you can drill down at the well level information here. So here is your casing, your well, and the formation tops, and all the inclination and the trajectory information here. So then you can also look at, say, for example, if you have well logs, you can now look at, so as the data is being moved, because if there is a well header, we can process all that information and populate it like this. And then you can do a QC with your domain expert. So for example, here, you have, I'm selecting the same basin here. So now you have all the different data types. For example, if you look at the gamma log, so you can look at this information here. And this is the summary. So you can do a quick review. And you can operate. So for example, if you want to cleanse the data, if you want to do any kind of smoothing, so you can have these kind of operations here. So the idea is, once you aggregate the data in a systematic way based on the standards, now you can apply different transformation techniques and aggregate all the information together, because each of them are correlated with each other. So you could also look at the core samples. Let us say, for example, if you have the core data. So here I'm selecting, so one of the, this is a good example of why, where there is no standard and you have all these images which are implicitly related to a wellbore. So there is no real standard for any core data. But since we are able to now map, like a core is associated with a wellbore and it can be correlated with a well log, so you can have those implicit relationships. And then as you're maintaining those relationships, you can now switch between different data sets. And especially for the newer data sets, you'll be able to now correlate against the hierarchy, which in this case would be a basin, well, or well. So that's how you can look at all the different well informations. I would now go to the seismic processing. So this is an example where you have on-prem data. For example, thanks to Equinor for providing the Vault data set. So what we have done is we have moved the Vault data set from on-prem to cloud to S3 bucket through Amazon Glue. So let me connect to the S3 bucket. So this is the S3 bucket where I have the Vault data sets and I have the seismic here. So I've just taken one of the examples of the seismic trace, the seismic velocities, the migration velocities. So the idea is we would now mount the data from the S3 bucket onto the Databricks cluster, which is the Spark cluster, and we would process that information and then transform and compute and extract that information so that we can now start analyzing that information. So now I'm going to log into the Spark cluster. So this is the Databricks interface. So here you have the different cluster options here. So when you create a new cluster, so for example, you have the different options. Here is where you have the worker node and the min and maximum worker node, and you have different options how you can configure your cluster. So you have the memory optimized, the compute optimized, just like how I described. You have storage optimized. So depending on what you need, depending on the job, you can have these different clusters. And also, this is a managed service. So this is basically something that you can run on AWS or Microsoft Azure. Okay, so let me go through a seismic example. So this is an example that reads the wall seismic dataset. So I'm just going to run through the notebook. I'll just explain and run through the notebook here. So what we are doing is we are running through a size, like we are reading from the S3 bucket here. So what is right now doing is this notebook is running on this particular cluster. Okay, so first time it takes a little bit of time. So while that is starting up, so this is the S3 bucket. So I'm reading the contents from the S3 bucket. You see all of this information here. And then I'm printing those content information here, like the wall data set, and this is the data set that I just showed you on the S3 bucket. So then I'm going to process, so there are two parts here. One is the Databricks itself has a cluster, as a storage mechanism, like a file system called the Databricks file system. So you can have that file system to do the processing. So sometimes the network load, depending on how S3 is connected, you will have some issues. So in this case, if you have a really high compute, you can do process at the Databricks file locations. So now I've started running this notebook. So I'll run through the S3. So I'm reading the S3 bucket now. So here is where I've read the data that is mounted in the S3 bucket. So I'm reading the contents of the wall data set now. Okay, and then here is where I'm copying it to the local Databricks file cluster. And here, for example, I want to read the data into different kinds of output files. So I'm specifying what are my intermediate files and what are my output files. So ultimately, the goal is to transform this information into HDF. So that now we can read, like for example, the idea is if you see the REST-HTML format, it's based on the new HDF. It's optimized for rendering. And also if you see the latest ProdML structure, it's also based on the HDF format where you're looking at the DAS images in HDF. So the purpose of HDF is optimized for, especially for scientific data storage and also for scientific data visualization. So here I'm specifying the H file, the output files. So while so then I'm cleaning up any kind of information that my previous data sets. So I'm now reading, this is a mechanism to read the segue header, and I'm reading the trace headers. And I'm appending these traces. These are all the mechanisms. So now I'm going to read the trace data. So in this, let us say this wall data set has about 300,000 traces, 340,000 traces, this particular file. So I'm now reading the trace data. So let me read the trace header now. So these are the number of traces, 348,000 traces. So I'm reading these trace headers, about 10,000 traces. So while that is reading, I'll just go ahead and explain. So ultimately, what the purpose of using the Spark is I can now read these as data frames. So I can do in-memory computing. I can do lots of processing of CDPX, CDPY using the seismic attributes. So I can compute new seismic attributes. And here is where I can run all the traces. I can read the header. And ultimately, I'm using all the transformation approach right here in the notebook. Like using the Python code and using the Spark cluster. So ultimately, what it does is, in the interest of time, I'll just finish it, this part. So we are reading the data sets and we are moving into the cloud. So, and then this is moved into the wall data set into the S3 bucket. So here's an example. So these are the HDF files that you can see. So when you download those, so you can now see these data sets as a data frame. So these are all the different data sets that you would see in the HDF information. Okay. So once the data is migrated once it's processed into the Spark cluster, you can now visualize this information into the cloud through an integrated workflow. So now I'm going back into the portal. So you can perform these kind of contextual visualizations. So for example, here I'm looking at the production data. So you can look at all the different kinds of GIS information, like the gas storage and all of this information here, the sedimentary basins, the product lines, and you can see all these visualized. So what we are seeing here is a bunch of wells. You have the shale plays, the sedimentary basins, and also the natural gas pipelines and the storage mechanism here. And then you can also look at the well production. these are the different well productions here. So you have by formations, by zone, all of this information. So you can do these kind of contextual data analysis. And then you can bring in the subsurface data also, the things that you have, the horizons and faults that you have moved into the cloud. So here is where you're loading all the faults and DFNs here. So you can see the subsurface information here. So idea is now you can bring in all the information together into some kind of a interactive dashboard where you can do more analysis. And then you can also integrate with external data sources like OSFI and those kind of other information where you're looking at the bottom hole pressure, the bottom hole temperature, and all these different kinds of information. So there's another view, like here is an example where you would look at the wall dataset all in one view with the seismic that has been just processed. So here I'm loading all the different wells from the wall dataset. I have all the horizons. So these are all the different horizons here. And then I'm going to import my seismic. So those are your seismic horizons here. So now what I could do is I could apply different color maps and look at the structure, how the structure looks like. So you can apply different color maps here. And then you can also look at the horizons here. So I'm turning off the different horizons. And each of these horizons are actually a mesh. So here is where you can look at different color maps here. You can apply the color maps. So you can see all the different wells, again, the formation tops and everything here, all of this together. So now you have brought everything together. So if you had the reservoir grid, like for example, from the external sources where you have the reservoir property like the geobodies model, you can also upload this information together. So this is an example of how you are bringing everything together. Then you can also perform any kind of analysis. So for example, if you have a geomechanical model, so you can do this kind of analysis here. So this is an example where you have a specific workflow. In this case, I'm computing the data. I'm preparing the data that is required for a near wellbore geomechanics. So what you're seeing here is the lithology model, the casing, the inclination, and also the trajectory of the well. And then you can look at the composite. So if you have data from multiple runs, you can composite all of the data into a set of unique data set that you can use for computation. So you can define your lithologies. So the idea, what I'm trying to demonstrate is once you have all of this data, you can now build a streamlined workflow for any kind of interpretation. And you can also do, say, for example, in this case, for the geomechanical model, you can do a breakout calculation and things like that. So here is an example where you are looking at how the well is failing at a given depth, and you can do any kind of mud window analysis and so on. So the takeaway I would say is the cloud and edge is basically providing a mechanism to manage, visualize, and data together in a seamless manner. And large-scale computations can be performed at scale with HPC and the Spark cluster available as a microservice. So all of the setup is delegated to the cloud provider, and the operator can focus on the business. And more importantly, you have all these machine learning models that can be operationalized. So together, this provides the insights, the necessary insights to unlock the full potential of the hydrocarbon reserve. Thank you.
Okay, so we have several questions. Thank you so much for your presentation. Let's see. So First question is, can we extract data frame to CSV file? And can you show how that is done?
Yeah. So yeah. So here is an example. I'll show you. There are many things you can do with the data frame. So the main thing what you should understand is Spark is good for data sets like Seismic because you can use it as chunks. But if you're looking at a boundary condition problem like a simulation, it will be a little bit difficult to manipulate the data. So Spark has support for text files, for JSON files. So actually, we are generating a text file just to validate the data, like the seismic header. So if you look at the S3 bucket that I just showed you, we are generating a text file from the cluster. So the transformation is from a Spark data frame, which is a PySpark frame, to a pandas frame, and from the pandas frame you can generate a text file. So here is an example where we are converting. I think, yeah, essentially I'm unable to find the example, but you will be able to convert the PySpark frame into a pandas frame, and then you can do all the transformation. And the good thing is, once you have the data, you have the mechanisms like you will be able to directly read. Like here, I'm reading the entire JSON object or a text file directly into a data frame, and then I'm able to display that information here. So anything that you're doing large scale columnar, so you should forget about doing like a for loop of doing all of this in a for loop. You should think everything as columns because this is big data computing.
All right, next question is, how do you design the structure of the database, especially to store metadata information? Do you use any standards as a reference, for example, PPDM standard, or do you have your own database design standard?
Yeah. So one of the big challenge is the standards are always evolving, right? And so what we have done is we have looked at the energistic standards, we have looked at the PPDM standards. So depending on the problem, because to implement these standards fully, it takes a lot of effort. For example, if you're taking the well information, instead of trying to come up with our own data structure, we would use the energistic standard. But sometimes if you take the standards as it is, they're not optimized for processing that information. So you can now come up with your own structure. For example, if you take the HDF data structure, it all depends. You can be really creative of how you arrange the data. So for example, we have been working with a major operator where they define the 3D grids of how you do the IJK computations. Right? Like Repsol has done a lot of high performance computing using the HDF as the data structure. Same thing for the well log information, you can have all of the information together. So the idea is you don't take the standard as it is for optimization, but when you exchange information with other vendors, you have to ensure that you are pushing the data to a standard, because then they won't be able to read if you give your own data standard. And one more thing on the standard is it comes up with lots of overhead. Like for example, if you take a well information, if somebody is looking at a production data, they don't care where the basin is. I mean, ideally they should care, but when they are doing their interpretation, they don't say, just give me the well information, I just want to do this processing, right? But as it becomes, as the data gets scaled up, then the organization has to look at, okay, you need this relationship. So whoever is implementing that information, it has to be properly tied up to the master database. So the summary is you do a loose coupling. But when you exchange, you should exchange with standards.
The follow-up question to that one is, since managing various subsurface data is very challenging, how do you manage to solve problems like incomplete metadata information from the data source?
Yeah, so again, that's where the business rules comes into play. So for example, a simple example would be like a well log where you have a certain section, there is null information there. And you have these duplicate formations. So there is no easy answer. What we would do is we would tag. So for any computation that you do, you would go back to the history. So as long as you tag the information, at least you can identify the problem. If you see a big spike in your rock strength, then you know something is wrong at the depth location. Then you should be able to easily trace back to the data, the source data. So we use a bunch of tags to manage that information, and the idea is at least track the source of the data and use your techniques like filtering, fill-ups. Like for example, you can fit a curve for the missing data. So those kind of techniques we would use. In some cases, when the data is too spiky, you can do smoothing techniques like mean averaging, those kind of things.
Okay. Does the Python code read Seismic? The Python code that reads Seismic, does it come pre-installed in Databricks?
No. You have to write your own code. Yeah. So Databricks is just a mechanism. It supports Spark, like Python, as I said, like different languages. So you need to write your own logic. So we wrote yeah.
Okay. Are you limited to curated data sets, or can you create your own data types such as formation pressure, real-time pressure, temp data,
yeah,
etc.?
So the HDF is a very fascinating format. That's why it's called hierarchical data format. So I can maintain the relationships across the information, and I can store any kind of double, float, string, anything, as long as you conform to the data standards. You can store any kind of information. Like if you see, HDF evolution came from NASA when they were using the satellite imaging. So it's ideally optimized for seismic visualization, for DAS visualization, and that's the reason probably REST-ML format is using the underlying HDF file. So it's an open format, but then like organizations like OSDU and Energistics, they are saying this is how you could store the data, and HDF is just a format. Same thing, you could use object storage like Ceph, where you can have distributed storage of the information.
Here is a perception question. So what is your experience on data science analytics reception by all companies?
I would say, I mean, data science is a great tag, but essentially anybody who's a STEM major, I would say he's a data scientist, because I mean, it's just, I think what you need to know is tools, how to use the tools. And more, I think the biggest problem with the data science is the interpretation. Like at the end of the day, you come up with a mathematical model. How does it make sense? So how do you apply it for which model? Because most of the machine learning models are in public domain. Like, because if you see whether it's retail, you're applying the same kind of techniques. I would say not to downplay the data science, but you need to really understand your data, and you need to prepare the data in such a way that you can now apply all these machine learning techniques. And not only that, you should, as an organization, you need the ability to deploy these machine learning models, or else it will be some kind of Python code that is sitting on a specialist desktop, or his own Python code that is not operational. So the key thing is understanding the data really well. How do I take this machine learning model and deploy at scale across business units? And that's what these cloud tools are enabling, like AWS SageMaker is one of the examples. Microsoft has the ML Studio, and Databricks has the ML Flow that is actually providing that mechanism to deploy these models and bring it to life across the business unit.
How do you get the DFN model?
So the DFN, again, these are the fab formats, the standard format that you would get from any of the standards. So either we use, most of it is coming from the REST-ML model.
What about marine conditions?
Sorry?
Marine conditions.
I didn't understand the question.
Well, it's very broad, so perhaps the person can elaborate a little bit more. I think they're trying to include, like, for offshore data.
Oh, yeah. So long time ago, we worked with an operator where they were looking at the shallow seismic to look at how does the rig sit through for an offshore platform. They were looking at the stability using the shallow seismic data. So yeah, the good thing is you have all the tools. as long as you really understand the data and you understand how the distributed computing works, you can now take all of this information and apply different. So the tools are there. So Spark and the data for like formats like HDF file that are ideally optimized for scientific data. So again, you can store text, all kinds of information. So so the takeaway would be, if you really understand your data well, you have the tools to implement that at scale.
Okay. There's a couple questions about data sets. One is the person is working in a personal project and they need to find good and reliable data sets. Can you recommend some source so they can go get CSV files?
Yeah, I mean, the good thing is Equinor has provided this wall dataset, right? So it has seismic, it has well logs, all of the information. So it's, I think, about 4 to 5 terabytes of information there. UK government has provided like 138 terabytes. So you can take whichever you want. These are public datasets, and there is one dataset from New Zealand where I can probably follow up. I don't remember, but there are public datasets that you can use. So just to test your seismic thing, right? USGS has a ton of information. Again, it's not something that you can use, but you can use the formats to test. That's how we tested the seismic parsers and all of that with USGS. And there are a lot of public data sets where you can get the well information. You may not get the actual well data, but you can really build new things from out of this. Like Canada has a lot of data. You know, they're public, like AER data, Alberta Energy Regulator, they are publishing all the information. So it's, I mean, you have wealth of information like world stress map. You can look at the geomechanical data, things like that. So to start with, wall data set, the UK data set, again, you have to drill through the information. You can start with those things to begin with. Like if you want to do any kind of well log analysis, you can do that.
All right, we're coming close to the top of the hour. I want to thank you, Sashi, for a wonderful presentation. There are still a little bit more questions on the Q&A box. We'll try to address those later through a posting.
Yeah.
We want to thank everyone for participating. We have people from all over the place, Nigeria, India, the US. So I want to thank everyone for your attention. I want to remind you that we're open for abstracts. So if you are working on data science, please go ahead and submit your abstracts for this event that is happening February 21st through the 24th. And we hope to see you there. Our next webinar will be Python for beginners on August the 27th. So we hope to see you there as well. Thank you, Saji, once more.
Yeah, thank you all for your time.
Bye.